Hello, welcome to everyone in this video. This is our lecture number 6 of electronics, and this is the first lecture of the BJT, that is the bipolar junction transistor and its biasing. So in this video I want to discuss about the all transistor type and their operation mode, and they are in the operation mode there is separate region that will be discussed, and then DC load line and Q point will be discussed here. If you want to watch the previous lecture, you can go through the description box. Link are given there where we will discuss about the different theorem, and then the diode already discussed. You can see this is the syllabus for University of Calcutta 4th semester BSc Physics Honors. This part, that is the circuit and network, discussed in lecture 1. Then the semiconductor diode and application discussed in the lecture 2, 3, 4 and 5. Okay, and these two part in the last lecture, I think 5, will discussed. In this lecture, that is lecture number 6, we want to discuss the bipolar junction transistor, that is the part A. That is consists the NPN, PNP transistor, characteristics of CB, that is common base, common emitter and common collector configuration. Then physical mechanism of the current flow, the how the current flow or the component of the current flow are will be discussed, and the current gain, that is alpha beta, and there are also gamma available for the CC mode. So current gain for alpha, that is for common base, beta for common emitter, and the gamma for common collector, and the relationship between, and then discuss about active region, cutoff region, saturation region, and finally concluded with the DC load line and the Q point. Okay, and the upcoming portion we will be discuss this portion, that is biasing part. So today we will be discussed this one. Clear? So this will be discussed here. In the upcoming session we will be continue with the FET, that is field effect transistor, regulated power supply, amplifier, feedback amplifier, and off amp, and then multiplier oscillator. This will be discussed in upcoming session, right? So if you want to previous lecture and the total playlist, you can go through the description box. Link are given there, and there are different playlists for the different part of the physics, theoretical and some problem solution. You can go through the description box. You will be get different playlist. Okay, so let's start with transistor. In the previous lectures, we learned about the diode. That is, diode means there is two terminal. There was a two terminal. That is, the one side was P and another side was N. P means there is a trivalent doping. The doping is trivalent, right? And in the N side, the doping is pentavalent. Okay, and there is only junction, barrier junction or depletion region. This was the case of diode. In case of triode or transistor, there is two junction. This will be like that. You can say there is two junction like that. If you consider this one, there is three terminal available here. This can be PNP, or in the other option, this can be NPN. Okay, this is written as E, that is for emitter. This is written as base, that is for base, and this is written as collector. This is emitter. This is base, and this is collector. So you can see here there is two junction. One is emitter junction with respect to base, and this is the collector junction with respect to base. You can write down this with respect to base, otherwise you can just write JC, that means the collector junction. So you can write here, that is JEB, that is the uh, junction between emitter and base. So the junction between emitter and base is the JEB, and JCB, this is the junction between collector and base. Junction between collector collector and base. This is known as the JCB. Depending upon this junction base, so junction forward or reverse, there are different name regions right here. Okay, here the transistor have two property, that is the width distribution. You can see these are symmetry like that. You can see there's a PNP, or in this side you can say this is emitter, this is collector, but there is a basic difference in terms of width. The width of the collector is larger than width of the emitter, than width of the base. So in terms of width of three region will be like that. In terms of doping concentration, you can see this order will be: doping concentration of emitter is larger than doping concentration of collector, then doping concentration of base. This is the order of doping concentration in three region. Okay, the transistor can be made by like that. You can take a base material, that's p type, and if you take the layer on n type and then layer on n type, this is NPN transistor. This is the simplest method. Otherwise you can take a silicon bar. This is the bare silicon. If you take the silicon bar and doping in the three different region with the different material, that is the in this you doped the trivalent. This is trivalent, this is pentavalent, and they are also pentavalent. So you can see in the trivalent, so this will becomes p type and this two becomes the n type. So in this process you can also find out the transistor. So there is different fabrication method to find the transistor, and the basic things is that there is three terminal: emitter, collector, base. The collector width is larger than emitter width, then base width, and the doping concentration of the emitter is greatest, followed by collector and the base. Okay, these two is main fundamental contribution of this transistor order of this. Now, depending upon this forward or reverse, you have a three region. You can say junction and the region. You have three region depending upon this junction. There is two junction J, E, B, and another one is J, C, B. Clear? J, E, B and J, C, B. First one is the active region. Active region means both the junction are forward bias. So both the junction are forward bias. If both the junction are forward bias, then this is called active region. Next one is the saturation region. Sorry, both are forward, so this is saturation region. Sorry for mistake. In the saturation region, both are in forward. In active region, JEB, that is the junction between emitter and base, is the forward bias, and junction between collector base will be reverse bias. This will be the active region. And then cutoff region, both are in the reverse bias. So depending upon the reverse bias and the forward bias, the uh, region of a characteristics of a transistor, naming as that saturation when both are forward, active when JEB, that is the junction between base and emitter, will be forward, and the another junction, that is junction between collector and base, will be reverse. And in cutoff region, both the junction is reverse. Okay, so this must be remembered of three region of the transistor. Now comes into the circuit symbol. Okay. The circuit symbol of transistor will be like that. This is the circuit symbol of a transistor will be like that. Okay, but the basic difference is that there is two type of transistor you just discussed, that is NPN or PNP. If you return, this is emitter, this is base, this is collector, emitter, base, collector, you have to take a arrow, you have to take a arrow between emitter and base junction in forward direction. If you take, this is PNP transistor, so in forward direction the current must be flow from P side to N side, so circuit symbol will be like that. If you take this as NPN transistor, then the current flow in this region will be P to N, so this one. So I think clear about when this arrow. So this is PNP transistor and this is NPN transistor. Okay, PNP transistor and this is NPN transistor. Okay, so you can see by denoting this arrow you confirm this junction is emitter base junction and the direction of arrow is mentioned, whereas this is NPN or PNP. These two are the circuit symbol. Clear? There is mode of operation. You can see this is a transistor basic. Okay, there is mode of operation will be like that. Three mode of operation available. Mode of operation. Three mode are operation available here. Number one, CB, common base. CB. With the naming CB, you confirm that is the base is common between input and output. The circuit will be like that. If you draw the circuit is like that. If you take, this is PNP, so this is emitter, this is base, this is base, this is collector. So you can see here that is this is input and this is the output. So you can see here in the input and output this base is common. Here you can see the voltage VBE. You say this is, sorry, VEB, that is voltage of E with respect to B, and VCB, that is the voltage of C with respect to B. So you can see here the base is the common here, that's why this is called common base circuit. In the circuit actually voltage is amplifier. This can be said as the voltage amplifier. Voltage amplifier. This circuit actually used for voltage amplifier. Next is the common emitter. Common emitter CE. Okay, so CE circuit, so you can draw these things very easily like that. If you take this an arrow, so this is emitter, this is base, this is collector. So the input and output, in the input and output the emitter is common, that's why this is called common emitter. Here the voltage can be written as VBE, that is the voltage VBE, that is the voltage of base with respect to emitter, and here the voltage will be CE, that is the CE, that is the voltage of collector with respect to E. So E is the common here, that's why this is called common emitter. And the use of this actually current amplification, used for current amplification. And third one is the common collector CC mode. In the common collector, the circuit diagram will be like that. The collector will be common, so this will be emitter. So this is collector, this is base, this is emitter. So this is input, this is output. So you can say this is the base with respect to collector, that is the voltage of base with respect to collector, and VEC, that is voltage of emitter with respect to collector. Okay, here the collector is the common, that's why this is called common collector. Okay, uh, this actually very high current amplification. uh, this application will be later on. Okay, so I think this all about the all are clear up to that things. If there is any doubt, you must comment in the comment box. Go to the next portion, that is the current component within a transistor. So this is a transistor, PNP transistor. You consider PNP transistor. Now, if you take that is all inward current as a positive and outward is negative, so this junction JE with respect to B, JC with respect to B. So we just eliminate the B as a common part. So this junction must be forward bias. So P side is forward, that's why this is high voltage, and inside is reverse, that's why this is low voltage. Clear? Here the current will be two component. For in P side there is a majority carrier hole, so the current flow due to hole is IPE, whereas the minority carrier is IN, so the current flow due to electron in this region is this. So total current IE must be the addition of these two current. This current is due to hole, and that is the majority carrier, and this current is due to electron, that is the minority current. So addition of these two current will be the total IE, that is the emitter current. In the region there is a component bypass through the base and the other component comes through the collector. Okay, so in the collector there are also p sides of the whole current, and this difference will be coming through this base region. And you know, in this active region, this junction is in the reverse bias. This JC junction, that is the collector base junction, is the reverse bias. So there must be a reverse saturation current, that is denoted ICO. It has two component due to hole and due to electron. Okay, so these are all the components of current flowing within a transistor in different mode. Common emitter, common base, common collector, there are same things, just the naming of this current and voltage will be different. Okay, and these two are junction. You must consider this in the current flow in the active region, and in the other two region the value of the current will be negative, positive, etc, etc. Okay, so you can see that is the IE equals to the addition of these two things, and ICO is the addition of these things. The direction is the opposite to that one, that's why negative taken here. And IC is the addition of these two things, the ICO minus ICPO. Okay, IC is ICO minus this one, and IPC is the IPC1 plus IPCO. IPC1 and plus IPC1. So this is the component of this. So if you define the alpha, that is the current in the output current, and this is the input current. Output current is the input current, and these are in the opposite direction, IC and IE, IC and IE. That's why we take the negative here. Okay, negative here. This alpha is depends on the emitter current, i.e. collector voltage, collector base voltage, ICB, and the temperature. Upon these three things, this alpha value is changes. And in the general form, you can see this alpha IC equals to minus alpha IE, plus ICO, but in general form this will be the form. Okay. Now, if we wants to find out the relation between alpha and beta, the alpha is nothing but the current gain in common base mode. So, in common base mode, you remember that is common base mode, common emitter, common base mode. In the common base mode, the output is like that, and this is the input. So, the current of the output is IC, and this is IE. IC and I. So this is IC and I. That's why this is the uh, base mode, IC by I. The effective current is IC minus ICO, reverse saturation current. Because this is very low, so you can write down these things. Okay. So in common base mode, the current gain is alpha, denoted as alpha. In the common emitter mode, this current is denoted as beta, and the net current will be the minus of the reverse saturation current, minus of this reverse saturation current. So this will be the IC by IB, that is the beta, that is the current gain in the common emitter mode. And in case of the common collector mode, this becomes gamma. So from here, the KVL, you can easily write down this IE equals to minus IC plus IB. That is the summation of three current flow within a transistor must be 0. At a certain point, the addition of these three will be 0. So I equal to this. So again, you know, IC equals to minus alpha E plus ICO. I know this thing. Okay. So if you use this, that is the alpha E equals to this one. So I equals to that one. If you compare these two relation, you can finally find out IB equals to 1 minus alpha by alpha IC minus 1 by alpha ICO. Since this alpha ICO is very small, so you can write down this thing. So this is nothing but that one. So IC by so IB by IC is defined as alpha. Beta is the IC by IB. So IB by IC is nothing but 1 by beta. So you will get the relation between beta and alpha. In the reverse form, the alpha equals to beta by 1 plus beta, and beta equals to alpha by 1 minus alpha. So this is the relation between alpha and beta. That is the alpha is the current gain in common base mode, and beta is the current gain in common emitter mode. Okay. In the different form of this IC and IB in terms of beta and alpha, you can write down this IB equals to like that, which already obtained here. IB equals to like that. So if you just put this value of taken the value of IB of like that, you can see here IB and IC related here. Okay. So if you use this relation, you will finally find out this relation. So IC equals to beta IB, that is the normal, and this is for the minority carrier current. Okay. Now know about the three mode of operation: common emitter, common base, common collector. So in common emitter, this is actually the circuit arrangement in the practical room. You need to, this is a potentiometer, these two are potentiometer. You can just vary the voltage, and you can see that is the emitter is common between input and output. This voltage is the input voltage, this current is the input current. This is the base, that's why this is written as base current. So here the base current is the input current, and the voltage at that point is the voltage of the base with respect to emitter. Voltage of the base with respect to emitter, this is the input voltage. The other side, this one is the collector current, this one is the collector current, IC is the collector current, and this current is the, this voltage is the voltage of collector with respect to emitter, that is the output voltage. So these two are output parameter, these two are input parameter, and the potentiometer or the pod actually helps to changing this voltage. Okay, so the variation of the voltage of these two region will be controlled by these two potentiometer or pod, and accordingly the current will be changed here. Okay. So for this circuit, because this is the emitter will be the common between input and output, that's why you can say this is a common emitter circuit. For this common emitter circuit, the inputs are these two things and outputs are these two things. The input characteristic. Input means the input voltage versus input current. You know that is in active region, this junction in the forward bias, this junction in the forward bias. So in the active region, the input characteristics will be like that. This is a forward region curve, the input voltage, input current. So this is the forward region curve. So you know the forward bias curve of a PN junction will be like that. So if you increase this voltage, the saturation or cut-in voltage will be increases. The cut-in voltage will be increases because this actually enhance the depletion region of this region. Okay, because this is a reverse bias, so this will be enhance the depletion region. That's why the cut-in voltage will be increases. Why this cut-in voltage increases? Because the depletion region increases due to reverse bias. Depletion region with increases as in reverse bias. That's why input characteristics will be like that and cutting voltage increases. Next one is the output characteristics, that is the cut-in voltage, saturation in active region. In the output characteristics, so in the output voltage and output current actually denoted here, that is voltage VCE. You can see here that is the collector voltage with respect to emitter, that is VCE, and the collector current is the IC, that is the output current. This is the output voltage and this is the output current. This region will be the saturation region. Okay, the IB, when IB is 0, IB is 0, that means this current is 0, this will be the IB is 0, and then negative, if you take this as negative, this positive means this is forward bias, this negative means this is reverse bias. So if these two are in reverse bias, these two are in reverse bias, this is already reverse and this is reverse, so those two are in reverse bias, this is cutoff region. And the very beginning of this VCE, when the VCE is very small, when this voltage is very small, then this region is becomes the forward due to this voltage. So when this forward and this is already forward, this becomes both are forward, so this is the saturation region. So you can see here, this is saturation region, this is cutoff region, and in that region the emitter junction is forward and collector junction is reverse. That's why this is called the active region. This is saturation, this is active, and this is the cutoff region. Okay, so in cutoff region the IC will be like that and the current flow will be like that. Okay, here these both are in the reverse bias. In cutoff region these both are in the reverse bias. If we consider the transfer characteristics mean the input output. This is was output characteristics and the begin. This one is the input characteristics. If you combine these two, one that is input versus output, the IB is the input current. The IB is nothing but the input current, and the IC is nothing but the output current. So input versus output curve will be output current. Input versus output curve will be right down here. That is the input output. That's why this is called transfer characteristics, because this is a combination of input and output, right? Common base configuration now comes into the next point. Common base configuration, that is base is common between input and the output circuit. So the input characteristics will be same things here, the forward bias junction, and output will be like that, but this point starting is will be separated out here. When this region is forward and this region is reverse, so this is become saturation when this also forward, this is forward, this is forward, so this becomes forward only if we change this potential direction. That's why this is in the negative voltage. Okay, so the same things for common base. This is actually used for voltage amplifier, and common emitter actually used for the current amplifier. Okay, and next thing is the common collector. For common collector, collector is the common, oh sorry, I written here in the sorry, this is emitter and this is collector. This collector is common here between input and output. Between input and output, the collector is the common here. Okay, This is actually used for the voltage buffer, and current gain is denoted by this current of output. Actually, gain is nothing but the output current by input current. So that's why the output current IE and the input current IB. Okay, and the input characteristics will be like that. That is input current versus input voltage. This was the reverse bias collector. So that's why this is in reverse portion, and this in forward bias. So this will be the like that. So these three are the mode of operation: common emitter, common base, and common collector. Common emitter current amplifier, common base voltage amplifier, common collector that is the voltage buffer. Clear? Now comes into the point load line and Q point. What do you mean by load line and Q point? You think that is in the simplest form of the common emitter junction. You can see that is VCE. This voltage is nothing but VCC minus ICRC by KVL. Okay, in this loop, if you use this KVL, VCE equal to like that. If you rearranging them, you can see here this is along x-axis, this is along y-axis. So x by a plus y by b equals to 1. So this equation becomes like that: x by a plus y by a equals to 1. That is the intersected straight line equation of intersected straight line intersected straight line. Okay, so this become intersected straight line, and this line actually known as the load line. This is load line. How we can find out this load line? At that point you can see IC is 0. So in this figure, if IC becomes 0 at in voltage of VC, that is the VCC. Okay, and there is VC 0. So if VC 0 at a current that is the maximum current, that is VCC by RC. So if you find out these 2 points, you just add it to us, you will be get the load line. So previously we obtain output characteristics. The white color is the output characteristic, and this yellow color is the load line. The intersection of the output characteristic with load line is known as the quiescent point or operating point. That is the Q point. So in short, the Q point is nothing but is the intersecting point, is the intersecting points between output characteristics and load line. Sorry, yes, load line. No problem. The intersecting point between the output characteristic and load line is known as the Q point or quiescent point or the operating point. Okay. Why we need to know about the Q point? Because depending upon the Q point, depending upon the Q point, the amplification of this amplifier, actually transistor is the amplifier, that is the rectifier, and transistor is the amplifier. So how input are amplified in the output region, in what portion, this actually depends on this Q point. That's why you need to know about this Q point. How? For that, there is 4 type of classes: class A, class B, and class C, and class AB amplifier. Think clearly. This is our output characteristics, and we got, suppose this one IB 0, and this is increased like that. Okay, this is IB is 0. That's mean this is the cutoff region. IB is increased here, and so on. And the load line will be like that. If the load line will be like that, this is the load line. Suppose this is a load line. So these are the Q point here. If you choose Q point like here, if you choose the Q point like here, and if you giving the input voltage within that region, you can see here, that is, this is amplifier. Actually you need to scale up this thing. If you apply this input voltage, this portion is converted here, like that. So the upper portion in the lower and lower is upper, 180 phase difference. So the total input converted into output. This is input and this is output. So total input converted into output. Total input converted or amplified in output. This is known as the class A amplifier. This is known as the class A amplifier. When the total input converted into output, then this is called class A amplifier. What is class B amplifier? What is class B amplifier? When you just think this is VC common emitter and this is IC common emitter output current. So this was the output characteristics like that, and this was the load line. If this is the if you take this Q point or the operating point, then what happen? Then if you just draw the input will be like that. If you take this as the input, this is the input voltage, and you will be get, because this is a cutoff region, that is the reverse bias, so there will be the no output voltage in this region. So only we got this input voltage, so this upper side portion. So you will be get this portion only, the half of the circle you will be get, and this is not often in the output. So this is the input voltage and this is the output voltage. Okay, so in input voltage, in the output you only get the half of the input voltage. So in output you will get half of the input voltage. Since this is a half of the input voltage often, that's why this is called class B. And class AB is nothing but the lies between A and B. That means when this operating point is like that, if you choose this operating point here, this is the output characteristics, this is the output characteristics. Okay, and this is your load line. If you take the Q point like here, this is called QAB. If you scale QAB, then what happened? You can see, if you take this as a output characteristics, then what happened? This will be the input signal. This will be the input signal, and the output becomes, you can see here, this portion will be emitted. So this output signal, you can think this is a input signal, and in the output this region we obtained, but this portion is not obtained, like that. Okay, so this is the between A and B, between class A and class B. Okay, so this is for you can see this is 100%, this is 100%, this is 50%, and this is 50 to 100%. Okay, 50 to 100%. And next is the class C. Class C amplifier. If you choose the output characteristics like here, if you choose the output characteristics like here, class C, when this Q point choose here, QC, then what happen? Then the if you took, this is a load line, then this Q1, so you will be get like that. Only the below the 50% you will get output. Okay, so below this 50% you will be get the output. So if you take this one, this is the input, so you will be get this one, that is below the 50%. Okay, you will be get below the 50%. So below 50% of input converted or amplified in output. Okay, so this is known as the class C amplifier of these things. So I think clear about all these things. If there is any doubt, you must comment in the comment box. This is all about me, and this is my contact detail. You can connect with me at this Telegram channel. This is my online platform, and this is my YouTube channel details. Go to this channel, we get different physics related theoretical and problem solution like this session. If you learn something from this session, share this video to your friends. Either he or she also get benefit from this video. Subscribe this channel if you new in this channel. Those already subscribed, thanks for subscribing. Press the bell icon to get notification of upcoming videos. So take care. We'll meet in the next video as soon as possible. Thank you.